Good morning, chemists. This is the last time we're meeting in this capacity, and we're going to wrap up the discussion of the extra problems today, and then hopefully there's some time for questions as well. So, just to remind everybody, on Monday, this coming Monday, we have the final exam. Just to wrap up this entire course. Has been a long quarter, but there's an end to it, and that will happen at 10:30 on Monday. The exam is 2 hours. It will be conducted in Canvas, and it covers all material that we have touched on in this class. Okay, so that is on the menu for Monday. Today, I would like to remind you that homework 10 is due today at midnight. It is not a lot of work, but I think it is a good exercise, so please do it on time. We will not be doing this over the weekend. I'd rather have you focus on the actual final exam as opposed to fiddling with the homework. So please complete it today and get it over with. Also, we have office hours today from 4 to 6. These are my office hours. The TAs probably have some additional office hours as well. If you want to join this particular office hours, use the Zoom link for the class to enter the lecture. It's exactly the same link. So, and we will be answering questions, any questions you may have about the material. We can practice some problems. I haven't really prepared anything in particular, but I'm open to any feedback or any questions you may have. Okay, so that gives us ample time to address any outstanding questions. Are there any questions about logistics, folks, that I can address at this point? There's a question in the chat about whether office hours will be recorded. We can record it and I can post it. That's not really a big problem. So yeah, let's do that. It's a good idea. Does the exam have 27 questions? I don't know exactly. It's a little less than twice the midterm. It's a little less than twice the midterm. That's what you may expect. Okay. All right. So let's go back to the practice problems that we looked at this week. We had problem number 8. Here it is, and we discussed 8a and 8b already. Okay, so I'm going to continue with 8c. All right, so just to remind you, this is about a helium atom. Helium has 2 electrons, and in the first question here, those 2 electrons will both be in the 1s state, and in problem 8b, one of them is in the S and the other is in the P state. So we have this configuration, 1s1, 2p1. In question C, we still have that configuration, and we're asked to draw the energy level diagram and label the states with term symbols for this configuration. Okay, so this is a question that pertains to finding term symbols and kind of realizing which term symbols have higher or lower energy. Okay, so we have 2 electrons. One is in the S, one is in the P. So the S, which is the total spin, there's 2 electrons, they both have spin half, so I can make 2 combinations, 1 and 0. Half plus half and half minus half. Okay, so those are the only 2 combinations that I can make. The total momentum for orbital momentum is, orbital angular momentum, is the following. I have a 1s electron and a 2p electron. The 1s has L equals 0. The 2p has L equals 1. So I can make only one combination here, that is 1, because only 1 has a value that's not 0. Okay, so that's only one possibility here. So what do I get from this? Well, I get the following. I have now 2 ways I can make a combined angular momentum, J. I can have because this is L plus S, right? And then L plus S minus 1, and then L minus S at the end. Okay, so dot, 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 and then L minus S. Sorry, this is not really clear. I do this with the mouse, so it doesn't come out as nicely. So what we have for when S equals 1, we can have the following. We can have 1, because that's L plus 1, and then 1 plus 1 minus 1, and then the last combination I can make is 1 plus 1 minus 2, which basically is 1 minus 1, which is 0. So I have 2, 1, 0. Those are the combinations I can make when S equals 1, right? S equals 1, L equals 1, and these are the combinations I can make, 2, 1, 0. Right? Now I can also do the same thing for when S equals 0. That is an easy one, because L plus S can only be combined in one way, and that is simply 1. There's no other option, because S equals 0. So what do I have? I have the capital L is 1 in all cases. That means P. These are true for S equals 1. 2S plus 1 is 3, so that is a triplet state. And then the J goes there. This is also a P, 3 with a 1. And this is a 3P with a 0. Okay, and then the other option where S equals 0, I have, again, a P state, because the P is determined by the value of the total orbital angular momentum, which is still 1. But S is now 0, 2S plus 1 equals 1, because 2 times 0 plus 1 equals 1. And then J is also 1. So that is the other possibility. So I have triplet states right here, 3 triplet states and 1 singlet state that I have to fill out. Okay, so that's what I have to do. So we can do that. Let's fill them out in terms of their energies. So I have the configuration 1 S1, 2 P1. I find basically this state here, which is a 1 P1, and then triplet states, which are lower in energy. I have 3 of them. I'm going to draw them. They're not completely, I mean, the separation between these states are not accurate, but I'm just ordering them in which one is the highest and which one is the lowest. Okay, so the triplet states have lower energy. That's what we learned. And the lowest one is the one with the lowest angular momentum, total angular momentum, right? So the lowest J. So that should be the 0. That's here. And then 3P1, 3P2. Okay, so that is the ordering of energy of this configuration. So this is an excited state configuration. The ground state configuration is 1s2, that is only one state. Both electrons are in the 1s state, so the total orbital angular momentum is going to be 0, so that's an S. They are anti-parallel, so that's going to be a 1. And then the combined angular momentum is also 0, because both S and L are 0. So this is the ground state term symbol, and these are the excited state term symbols. Okay, so this term symbol here corresponds to this configuration, and this excited state configuration is having 3 different ways in which you can make that excited state, namely 1 singlet state and 3 triplet states. Okay, so that is the answer to problem C. Okay, now I'm going to move on to problem D. It says, write one of the triplet states of this excited state configuration in terms of a Slater determinant. Okay, so now we have to write one of the answers we found under B in terms of a Slater determinant. So I'm going to bring back the answers to question B. This is from last time. Okay, so this is the same answer from last time. That should still be in your notes, so you don't have to write it again, I think. And we found basically 1 singlet state. This is the singlet state, right? And then 3 triplet states. and here they are. Again, let me re-emphasize that in the singlet state, we see that by definition, the spin state must be antisymmetric, otherwise you cannot make a singlet state. Okay, that means that the orbital state is symmetric. In the triplet state, it's reversed, namely, the orbital state is antisymmetric, and therefore the singlet state is symmetric because all triplet spin states are symmetric states. Okay, so there's 3 triplet states. Now the question here is, write one of the triplet states of this configuration in terms of a slated determinant. So there's 3 of them, I only have to work with 1. So I'm gonna pick one that makes my life easier. Okay, I can pick any one of them, but I'm gonna pick one that is easy to do, and that's the first one. I think that one is easy to do because the spin state doesn't have a strange combination like the second one has this plus sign here that makes it much more complicated to write as a slated determinant. This one is fairly easy, okay? So what we do, we're gonna write this cross product here in terms of a determinant. Since every electron here has a alpha state, I don't have to worry about the alpha so much. I only have to make sure that this cross product from the multiplication from the determinant delivers this expression right here, okay? So, and that's what I'm gonna do here. It's called like this. So let's write that down. What I'm gonna do is I'm gonna find the wave function, the slated determinant, and it's gonna be a determinant which has a normalization factor which looks like this. And then the first spin orbital is an alpha. Okay, there's 2 different orbitals. There's a 1s, and there's also a p, which is going to be next to it, alpha 2p. And in the first row, I only have electron number 1. And in the second row, the same for electron number 2. Okay, so this is electron number 2. All have alphas, because that's what I chose. I chose the easiest total wave function, which only has alphas to worry about. That means every of these spin orbitals has an alpha in it. Okay, so this is what I'm getting. And so I should multiply this one with this one minus this guy times this guy, and then all of them have alphas. And that basically indeed regenerates the option that I chose. You can verify that this is the right slated determinant. Okay, so in slated determinant, the rows have the electrons, and then of course the spin states are indicated, and then the possible orbitals in which that electron can sit are the columns. Okay, so this is the answer to 8D. All right, so moving on to problem 9 then, and here we are dealing with making a molecular bond between 2 atoms called A and B. And we have, of course, atomic orbitals, and they're called little a and little b. Those are the 2 orbitals of the atoms, and I'm going to make a bond between the 2. Okay, so question A, it says the following: assume a homonuclear bonding between A and B using S is AB is BA. Okay, so S is not necessarily 0. Remember, we don't know, these 2 orbitals here come from different atoms. They don't form a complete set, and therefore I cannot assume that A and B, this overlap integral, is automatically 0. It's not, therefore it has a value S. Give a general expression for the normalized bonding and antibonding orbitals under which conditions are these orbitals orthogonal. Okay, so let's do that. What I'm going to do is I'm going to make linear combinations of the 2. Right, so I'm going to call the first one, let's say 1. It has a normalization constant in front, and then it has coefficients. Let's call this the coefficient associated with state A for wave function 1 plus B, coefficient for this atomic state, which is B. And this is a problem that we have done in class several times. And I'm just going to basically rewrite that, what I found last time. And that is the following. This is a normalization constant, which you can verify. Okay, so that is the normalization constant. And then we have, for this orbital, if the bonding orbital, CA1 and CB1 are going to be both 1. Okay, so in that case, I simply have this combination, which gives me my orbital. So this is my first bonding orbital. And I remember I have basically assumed that this is 1 and this coefficient is also 1, because that's what we have seen in class several times. So I'm not computing that. I'm not going to rehash the whole thing. I'm just going to duplicate what we learned and write it up. Okay, so that's what I'm doing here. Second one, call it 2, which is then probably going to be the anti-bonding. Okay, same way. So this is a general way of writing. So this is coefficient with a 2 here, which basically means it belongs to the second wave function. This A means it is the coefficient that belongs to atomic orbital A. And then 2B, okay, this one. And I'm going to do the same thing as before. I'm going to rewrite the answer we found. And we found this. Gee. This mouse writing is more tricky than I thought. This strange little thing is just a 1. There's no eraser, so I cannot do it. This is a 1. Sorry for that. It's really hard to write with a mouse. And this is the combination that we found in class that I'm restating here, where C2A equals 1 and C2B equals -1. Okay. So the question now is, when are these two molecular orbitals, which are now given by these two expressions, when are they orthogonal? And they're not automatically orthogonal. We have to consider the situation when they are. And they are orthogonal when this S is the same for each. So this is a plus S and there's a negative S here, but only when S equals 0, they're going to be equal. All right, basically you get cross products if you have these two orbitals and you multiply them. Let's just do it. Let's just do it because we want to make sure that everybody understands. So I'm going to put the first one and the second one. Okay, and I'm going to integrate that like so. Oh my goodness. Let me redo this because turns out that my mouse is starting to misbehave after I'm writing longer and longer. So I have to refresh the page so we get a better writing situation here. So what I'm going to do is I'm going to multiply the first orbital with the second orbital. Okay, so that is number 1. And let's do it like this. Number 2 times number 1. That's the same. That is one of the overlap integrals, so that's S. If this thing is 0, then they're orthogonal, right? So when this overlap integral is 0, then they are orthogonal. So we can just verify that and basically write, let's say, N2, that's the second normalization constant. This is alpha minus beta, and this is a star here. And then N1, and this is alpha plus, not alpha, A and B. Okay, so this is the integral I have to do. Now, I don't have to write this whole thing like so because I have the bra and the cat here. So I can just make this multiplication directly. What I'm finding here is the AA, that gives me this integral. I also have this integral. B, and then of course I have these combinations, A, B plus B, A. Okay, so that is what I'm having here. Now, sorry, there should be a negative sign here. Apologies for that. One of them is negative, one is positive. So if AA and BB both are normalized relative to themselves, 1 minus 1. That's good. And then here I have two overlap integrals, A and B. That's basically, that's an S, and that is an S. Sorry, this is the big S, which is the overlap integral between the molecular orbitals. This S is the overlap integral between the atomic orbitals. Just to make sure that we don't mix those up. So the atomic orbitals here come from different atoms, and therefore this overlap integral here and here are not necessarily 0. If they are 0, then this whole thing is going to be 0. Okay? Then this whole thing is going to be 0. So, but only if the overlap integrals AB and BA are going to be 0. And that is not necessarily the case. So that is basically the answer to this question. Under which conditions are these molecular orbitals orthogonal? They are orthogonal under the condition that the overlap integral between the atomic orbitals is 0. That is the answer. Okay. So next one, B. So what we have to do is, in the context of variation theory, write the secular equations for this problem. Okay, so this is basically just rewriting the steps we have done in class. And this is not a question you would find on the exam. Okay, so just want to make sure people understand that, because that's not really necessary to do. I think it's not a good question for an exam, but it is a good question just to kind of like understand what are the steps in variation theory? What do we do? Okay, what are the essential procedures to find solutions in the variation theory? And so we have to write down the secular equations, and in class, the secular equations were defined as follows. Okay, it's a sum over the coefficients, and then we have H, I, K, and then minus E, S, I, K. This is the definition of the secular equations. Okay, so that's the definition, but we have to write it out. The reason why we do this in this exercise is just want to make sure people know, what these secular equations are, one, and how to fill them out and find solutions from them. So how to do this is to realize that this I runs over all possibilities of atomic orbitals, which is A and B. Okay, so it runs from A to B. So I can be either A or B. That's one consideration. And then K can also be A or B. So I have the following situation. K can be A. And in that case, I can fill out one of these sets of equations, namely CA, H. So I is A, and K in this column is also A, because that's what I just said here. Okay. And then E, S, also A, which is going to be 1, plus, now I is going to flip to B, because that's the next one in the sum. And then I find H, now this is B, A, because K is still A, and then E, S, B, A. Okay. And I can rewrite this a little bit because I have definitions here of these integrals. So I see CA, and then HAA, which is this guy, is called alpha, so that's alpha, and then minus E. SAA is going to be 1. That's the overlap integral of the atomic orbital with itself, plus CB, and then HBA is this guy, which is beta, E, and now S is not 1, so it's called S, and the whole thing is going to be 0. So this is the first equation that I'm generating. Second equation is when K equals B. I'm going to do exactly the same thing. So I have CB, H, A, B, and then E, A, B. Oops, that's an S here, sorry. Plus CB, H, now B, I is B again, and then K is also B, so that's HBB minus ESBB. If you do this one time, then you see exactly how to fill this out. That's why we have this exercise in here. So there's no mysteries, hopefully. Oops, that should be an A. Sorry. Ca beta minus Es, and then plus Cb this time, alpha minus E equals 0. Okay, so those are the two possibilities that I'm having here. Okay, these are the cyclic equations that I'm generating. This is the answer right here. And this is something we can solve. Okay, and this is what we've done in class. And if you solve this set of equations, then what we find two energies. Okay, and these energies are the following. I find a plus combination where alpha plus beta and 1 plus S. And then E minus, that's the second energy that rolls out, was alpha minus beta, and then 1 negative S. Okay, so these are the two energies that follow from these two equations. The first energy is associated when the Ca and Cb are both 1, and the negative energy is associated with when Ca and Cb are not the same. They are the inverse of one another. Okay, so one is negative sign, the other is a positive sign. That is what generates this energy right here. And we've done that in class. We don't have to redo that here. That's not what the question is. The question doesn't ask us to solve these cyclic equations. It just asks us to write it down. And that's what we just did. But from these equations, you can generate these two energies. Okay? Okay, so that is question B. Now question C, it says assume alpha has a certain value, beta has a certain value, and S also has a certain value. Determine the energies of the bonding and antibonding orbitals and sketch the energy levels of the MOs in a diagram. Actually, for this, we do need these two solutions. We're not being asked to explicitly solve for them, but this question goes back to the lecture notes and assumes that you know that for this simple system, homonuclear system, there's two energies. One of them is alpha plus beta over 1 plus S, and the other is alpha minus beta over 1 minus S. Okay, so that is something that you would need to do this problem. So I'm going to write that down for option C here. I'm going to say this is my original atomic orbitals. They have values alpha. And then it's going to split into an antibonding and a bonding orbital. And I know that what I'm going to find is two energies. That's going to be alpha minus beta, 1 minus S. And then the energy here for the bonding is going to be alpha plus beta, 1 plus S. These are the two energies of the two states. Okay? And so what I have to do in question C is to fill out these numbers. Why? It's just a good exercise so you see that these alphas and betas actually mean something. They have units. They have units of energy, in this case, electron volts. Okay? So what I have to do is I just have to fill that out. So I'm going to fill it out, 5 minus 1. This is in electron volts. So the energy is going to be in electron volts. And then the S here is 0.1. And 0.1 does not have, the S doesn't have a unit. That makes sense because it's an overlap integral. It's just an indication of how much something overlaps. If it's 1, it overlaps fully. If it's 0, it doesn't overlap at all. And any value in between is a partial overlap. So that's what we have here. Okay, so we can just evaluate this and see what we find. We find the following number. In this case, if you do the arithmetic, punch it into your calculator, you find negative 4.44 electron volts. So that is the energy of the antibonding molecular orbital. Let's do the same thing for the bonding combination. Now I have to minus 1.0 That is the numerator, and then the denominator is 1 plus 0.1. Okay, do that, and we find negative 5.45. Okay, so you see that indeed, if you fill out these numbers, that the bonding orbital is lower in energy, that's what we expect, and the anti-bonding orbital is higher in energy, which is what we expect. Okay, so this exercise is good because you see that those values lead to sensible solutions, right? Sensible numbers. We do expect that the bonding orbital is a lower energy than the anti-bonding orbital. Okay, so with this we can move on to D. If S becomes larger, so if the overlap integral becomes larger, an overlap integral is defined as the overlap of the atomic orbitals here. Okay, A and B or B and A, that's the same. If this thing becomes larger, so if the atomic orbitals have more overlap, does the energy splitting between the MOs increase or decrease? Give a physical explanation. So what we have to figure out if this separation here between the molecular orbital energies is going to increase or decrease if the S becomes larger. Okay, so we can do that. 1 minus S, if S becomes larger, then the denominator becomes a smaller number, which means that this whole thing is going to go up. All right, so this goes up, but there's a negative sign in front. So this number here becomes a bigger number with a negative sign, so it becomes more negative. Okay, so it's minus 4.44, but the number value goes up with a negative sign means that the energy will go down. Okay, so it goes towards lower values, and that means it goes closer to, let's say, the bonding orbital. And then here, the denominator is 1 plus S, so if S becomes larger, then this number becomes larger. That means that this whole thing becomes smaller with a negative sign, so it becomes less negative. Okay, so this state goes up. So we see that the anti-bonding goes closer towards alpha. We also see that the bonding orbital goes closer to alpha, so that means that the energy separation shrinks. Okay, so it decreases. That is the answer here. So I have to have a small connotation here, because if you continue that, if you go from 0.1 to 0.2, then this is indeed what happens. But if you make it even larger, like say 0.5, then you run into problems. You will see if you do that, you get unphysical solutions. So this is kind of working only within a certain range. When S is small, if S becomes big, so closer to 1, then problems emerge. Okay, you get unphysical results. And this is important to realize, because remember, all of this happens within approximations, and we have to be aware of that. Okay, the variation principle is an approximate method, and so there's a limit to how well they work. And this limit for small s, they work well, but if s is going to be large, they will not work well. Okay, so this is the variation principle. Hopefully this confirms or reaffirms some of the stuff you already know. And I'm going to move to problem number 10, which is the last problem of this set. And it's about the Huckel approximation. Of course, we need to have at least one Huckel problem in there. It's about this molecule here, which is cyclopentadienyl anion. Okay, so there's a negative sign here. You see there's two conjugate bonds, and there's a negative charge there on this particular atom. So that is the situation. I have 1, 2, 3, 4, 5 carbon atoms that partake in this ring with their p orbitals. And I have 1, 2, 3, 4, 5 atoms plus an extra electron, so a total of 6 electrons. So 5 carbons that partake, 5 p orbitals that partake in this problem, but 6 p electrons that are partaking in this problem. So that is important to realize. Because of this negative symbol here, negative sign, means that there's an extra charge. So the number of p electrons is not the same as the number of carbon atoms that partake in the pi conjugation. The first question is to write down the Hamiltonian matrix within the Huckel approximation. Okay, so we do have 5 carbon atoms, and that means this is going to be a 5 by 5 matrix. Okay, so let's write down H. We have alpha on the first position, nearest neighbor, beta, and then 0, 0, and then another beta, because that's going to be the overlap of atom number 1 all the way around the circle and coming back. So that's again a nearest neighbor. Okay, so second one, beta, alpha, and then beta again, and then 0, 0, 0, beta, alpha, beta, and then 0. And then 0, 0, beta, alpha, and then beta, and then finally beta. That's the other combination of atom number 1 and 5. They meet again, 0, 0, beta, and then alpha. Okay, so this is the Hamiltonian matrix in the Huckel approximation. Okay, so that's step number 1. B, after diagonalization, the diagonal shows the following eigenvalues. This is a typical exam type question because we are not solving this thing either numerically or by hand on the exam. Instead, it says if you do that step, if you do the diagonalization, then you find the following scenario, namely a diagonal matrix with these things on the diagonal. Okay, so there's one value here, then there is alpha plus this one here, and alpha plus this one. So these are basically equivalent. There's a negative combination and a positive combination. Right? So there's plus minus or minus plus, which means there's 2 plus combinations and 2 minus combinations. Okay, so what I have to do here is to sketch an energy level diagram and fill out the orbitals with the available pi electrons. Okay, so what I'm having is alpha plus 2 beta, and then alpha plus 1 plus this square root of 5 over 2. This plus combination, so 1 plus square root of 5 over 2 is smaller than 2. And that means that the lowest possible energy, I call that pi 1, is basically an energy of alpha plus 2 beta. That is my lowest possible energy. The next lowest energy is the plus combination. So 1 plus square root of 5 over 2. There's also 1 over here. And that means I have 2 states that have that energy. I call them pi 2 and pi 3. And they have energy alpha plus, and this is the plus combination, 1 plus square root of 5 over 2. Sorry, this is the 5 over 2 times beta. Okay. And then I have a negative combination, so that's 1 minus square root of 5 over 2. So square root of 5 is larger than 1, so this is going to be a negative value. Beta is negative, so that basically puts it over the alpha line. The alpha line is the energies of the atomic orbitals. So there's 2 more pi orbitals. Call this pi 5, and this is pi 4. And these have alpha plus 1 minus square root of 5 over 2 beta. Okay, so because this is a negative value, it basically flips the sign of beta, and that's why it's above this alpha line, right? So all of them have, of course, energy alpha, and then either with beta, 2 beta down, and beta is negative, so it goes extra down. Then another value of beta, this is still a positive number. It means because beta is negative, you are on the negative side of the alpha line. And then here, because this 1 minus square root of 5 over 2 is a negative value times the negative value beta, that means you go up from the alpha line. So these are the 5 solutions that I have in terms of energy. There's 5 molecular orbitals, 1 over here, which is very low, and then I get 2 degenerate states, 1 below the alpha line and 1 above. So there's 5 molecular orbitals, there's 6 pi electrons, as I just said at the beginning of this problem, So I fill out 6 electrons, and that goes like so. Okay, so these are the 6 pi electrons, and you can see they are all in bonding orbitals. None of them is going to occupy an anti-bonding pi orbital. Okay, so that is indicating that this is a very stable molecule. It benefits very much from the bonding character of the bonding orbitals. Okay, number C, or question C, how many nodal surfaces through the ring do you expect for the wave functions with the energies alpha plus 1 negative square root of 5 over 2, which is basically these two guys. Okay, so these two guys I have to consider. And how many nodal surfaces do these two states have? They are the same energy. That means they have the same number of nodal surfaces. How do I figure that out? Well, it's very simple with these molecular orbital diagrams, because the lowest state has 0 nodes. The next one up, and there's 2 solutions of them, but since they have the same energy, they have the same number of nodal planes. They have 1 nodal plane, and the next one up have 2 nodal planes. So consequently, the answer to problem C is simply 2. Okay, 2 nodal planes. Where they are exactly, I don't have to draw here. That's not the question. I just have to recognize that since this is the lowest one, and then the second lowest one has 1 nodal plane, and so forth. So this is the state that has 2 nodal planes. All right, last one, this one. Do you expect this molecule to be aromatic? Okay, so how do we figure that out? Well, there's this very simple formula. It's 4n plus 2, which will be the number of pi electrons in this pi conjugated system, where n is simply an integer starting with 0, and then 1, 2, 3, 4, 5, 6, and so forth. Okay, so n can be any number as long as it's an integer starting at 0. So if I take n equals 1, n equals 1 will generate 6 pi electrons. And that means that I have 6. So I have 6, which means I fulfill the condition for aromaticity. Okay, so I do have the condition met for aromaticity, and that means that I have an aromatic molecule. So this seems counterintuitive, perhaps, if you look at it, but that is because it's hard to see exactly how this pi conjugated network works in this 5-atom system. The key here is to realize that it's defined by the number of pi electrons that partake in the pi conjugated network, and that is 6, and therefore it fulfills the condition for aromaticity. Okay. There's a question, how is it determined that n equals 1? And that is very simple. N is just an arbitrary integer number. And it simply says, if n runs from 0 to 1, I can have the following possibilities for systems that are aromatic. Namely, n equals 0 says 2. If you have 2 electrons in your system, you could be aromatic. Next one is 1, that generates 6. Okay, then you're also aromatic. So if there's 2 or 6 electrons in your aromatic system or in your conjugated system, then you can have aromaticity. The next one is 2, so 4 times 2 plus 2 is 10. The next one is 10. So molecules that have this number of pi electrons in their pi conjugated system, they are aromatic according to this so-called Huckel definition. Is that clear, folks? So this n is not related to anything. It's not related to a particular situation. It is just a generator of numbers, and the numbers are basically given here. If your molecule has any of these numbers in terms of its pi electrons, then it is likely aromatic. Okay, there's a question about 9D, that's over here. Oh yeah, if S becomes larger, does the energy splitting between the MOs increase or decrease? So again, what you have to realize is that the solutions are written as such. So it's alpha plus beta, 1 plus S. and then E minus equals alpha minus beta, and then 1 minus S. The importance here is that the denominators for the plus and the negative, these two guys, these denominators, are not the same. And that means if S is going to change, which is what we do here, or make it larger, then the denominators will behave differently for the two molecular orbital states. Okay, in other words, this one is going to go up the denominator, which means the value of the energy is going to go down. Since it is a negative, it becomes less negative. And here, this is going to be a smaller value when S goes up, which means this whole value is going to go up. And since it's negative, it becomes more negative. So this one becomes less negative, if S goes up, and this one becomes more negative. And so that means that this one becomes less bonding, and the E minus becomes more bonding. So that basically means, we just drew the splitting is shrinking in this case. So we get this one going down, this one going up, and the splitting energy between the MOs is going to decrease in this case. But I have a connotation there, and that is that this only works within a certain range. So S should be a value close to 0. If it gets very close to 1, this whole thing will fall apart. That is part of some of the approximations that we have made. Okay, so S must remain a small number in these descriptions, which usually is the case. So that's good. But if I make up a situation and arbitrarily change S to, say, let's say 0.5 or 0.6, which is pretty large, you will see that this description is not very accurate and becomes unphysical. So if you ever encounter that problem, then you know why. You have basically stretched beyond the approximations that you have made beforehand within the variation principle. Okay, somebody likes to look at question 10b again. 10b, what atomic orbital means? I don't see atomic orbital here. I mean, basically, what I said about this ring is that there are 5 carbon atoms, so there is 5 atomic p orbitals that contribute. So 5 p orbitals make up the pi conjugated system, but it has 6 electrons in it. So 6 pi electrons, 5 p orbitals. It's a 5 by 5 Hamiltonian matrix generating 5 states that then accommodate 6 electrons. Another question is, why is pi 5 and pi 4 above the atomic orbital? Well, that's simply because what I find. Okay, so it says after diagonalization, I find the following energies. This one is much lower than alpha. Alpha is basically the energy of the individual p atomic orbital. The molecular orbitals will have alpha plus or minus something. Okay, so in this case, it's 2 beta. Beta is negative, so that means you're going to have less than alpha. That means a lowering of the energy. That's basically the bonding. That's a bonding character. So if as soon as your energy goes below the individual atomic orbitals, that means you're doing better than the individual orbitals. That means bonding is more favorable than non-bonding, right? So that's a favorable situation. And then I have simply 2 possibilities. I have 1 plus square root of 5 over 2. This number is larger than 0. And then 1, it's negative 5 over 2. This number is less than 0. So it's negative, so positive and a negative number. So in one case, I subtract something from alpha, and in the other case, I add something to alpha. So in one case, I go above alpha, the energy of the atomic orbitals, and in one case, I go below. So in the case of pi 4 and pi 5, I simply have energies that are more than alpha. So that means anti-bonding character. There's a question about how do I know that I have 6 pi electrons? Because each carbon atom contributes 1 electron to the pi conjugate network. That's always the case. So I have all of these atoms here are neutral atoms. So they have 4 valence electrons because it's carbon, and I have 1, 2, 3 bonds, right? And then and then there's a 4th bond here. So this is of course an H sits here. So there's 4 bonds, but there's one of the electrons that partakes in this pi bond. You see? So each of these 4 electrons, each of these 4 carbons contributes at least 1 electron to the pi bond. So that's a total of 4 right off the bat. And then this guy here is negatively charged. Okay, so it has, as you can see, it has also 4 bonds. It has, yeah, it has actually here H, but it has an extra. Actually, this is not correct. Sorry, it has 1 H here, not 2. Okay. So it has 1, 2, 3 electrons used to make these bonds. Okay, and then 1 electron that is in a p plus an extra 1. So that's 2. And this one contributes 2. So that's a total of 6. Okay. So this is a total of 6 electrons that partake. The difficulty is this atom right here. And it is important to realize it's not really clear from the structure. That's something I guess you have to know. That this has 1 H here. Okay. And therefore, it will have 2 electrons available for the pi conjugate network. Yeah, that's another way you can do it. 1, 2, 3, 4, and then this on every carbon atom here, which is part of the conjugated network, contributes 1 plus 1 extra. That's 5 plus 1. That is also 6. So either way, you can determine that. Okay, folks, we are already past the 50 minutes, so I'm going to stop right here. I would like to remind you at 4 o'clock till 6 this afternoon, we have office hours. If you have any extra questions beyond questions addressed here today, please join us. And hopefully that will give you enough preparation. Okay? Thank you all.